everyone and welcome back to the course on econometric modeling. This is module 16. In module 15 we have discussed the problem of omitted variable. Module 16 also continues with that, but once we have discussed model misspecification in terms of omitted variables and measurement error, this module basically checks or suggests the corrections that need to be made in order to control the problems or this kind of model misspecification problems. So, first of all we introduce proxy variables. Proxy variables or PVs are used only when there is a omitted variable problem, but not in case of measurement error. If we know that the error term is not uncorrelated with x, then we use proxy variables. Continuing with the previous examples, that is the example that we discussed in the context of omitted variable, that if we have an equation or if log wage is dependent on education and ability, and in case we do not include ability in the expression. So, we know that z equals to ability, or if we denote ability by z, this is omitted and the error term becomes gamma z plus u. So, my original model was y equals alpha plus beta x plus gamma z plus u, say, where y is log wage, x is education and z is ability. Now, z is not observed and that is why the entire thing becomes my error term. If we can proxy ability with IQ scores, say, and we denote it by z star, which is a proxy variable for z, then z star will work under two conditions. So, first of all, this is my original model and the original model should fulfill this condition, that expected value of u given x and z is equals to 0. So, both originally ability and education were uncorrelated to the error term. Now, in order to include the proxy variable, we need to have basically three additional assumptions. The first assumption is that expected value of the error term conditional upon x, z and z star equals to 0. So, the proxy variable additional to the x and z variables is also uncorrelated to the error term. Second assumption is that expected value of z given z star is equal to theta naught plus theta 1 z star. This implies that we can conceptualize, or there is a linear relationship between the proxy variable and the variable which is omitted, that is here in this case ability and IQ score. So, IQ score and ability, or rather IQ score explains ability in a linear format, where theta 1 is not equal to 0, because if theta 1 equals to 0, then this implies that IQ score does not explain ability. So, theta 1 has to be non-zero in order for z star to qualify as a proxy variable or PV. And the third assumption is that expected value of z, that is ability, given x and z star is equal to expected value of z given z star. This assumption basically says that once z star, that is IQ score, is controlled for education, or x measuring education does not affect ability anymore. Alternatively, expected value of ability given education and IQ is equal to expected value of ability given IQ, which is equal to theta naught plus theta 1 IQ, right. So, this actually may not seem very realistic, or that may vary from situation to situation, but then this actually can be a close approximation to reality. Now, this is our population model again to begin with, y equals alpha plus beta x plus gamma z plus u, where covariance between x and u and covariance between x and z both are 0. Now, expected value of y given x and z star is equals to alpha plus beta x plus gamma into theta naught plus theta 1 z star. You can see that in place of z, z is replaced with z star, and since z is equal to theta naught plus theta 1 z star plus some error term, say u1. So, I am actually taking the expected value of y. We are having expected value of z equals to theta naught plus theta 1 z star, and that is why it is replaced here. And then by collecting terms, we have alpha plus gamma theta naught plus beta x plus gamma theta 1 z star. So, this is called the plug-in solution for omitted variable. The coefficient of proxy variable can't be interpreted as that of ability. The intercept also changes, but the advantage is that the coefficients of other regressors remain unchanged, or we get good estimates of the other regressor or other parameters. So, we can see that beta remains unchanged, though of course, the parameter estimate of z star is not equal to gamma, and as a result of which, because in order to z star in order for z star to qualify as a proxy variable, theta 1 has to be non-zero, and if theta 1 is non-zero, then gamma cannot be equal to gamma theta 1, as a result of which we do not have actually estimate of ability given by the alternative proxy variable, which is IQ score, and our intercept term also changes, but we most often are focused on or more concerned about the parameter estimates of the other regressors. So, the other regressors tend to have unbiased and consistent estimates, there is no problem. So, proxy variables can be used. Now, we talk about the other tool used in order to take care of both omitted variable and measurement error problem, and that is instrumental variables. Instrumental variables are applicable to the problem of omitted variables as well as measurement error. Let us first consider the omitted variable problem, where this is our original model. For estimation z, say ability is omitted for not being observable. If x and z are correlated, then estimation of y equals alpha plus beta x plus u gives us biased and inconsistent estimators, because you can see that this will be our error term, and the error term will be correlated with x, because x and z are correlated, right. So, we cannot have unbiased and consistent estimators. This has already been discussed in the previous module. But y equals alpha plus beta x plus u is still estimable if we can find an instrument for x, that is a variable, say mother's education. So, remember x was education of the individual. Now, we are trying to find out an instrument for the variable x. Suppose it is mother's education, and we denote it by z star, such that covariance between z and z star equal to 0. What I want to mean is that this is my error term. So, when I am replacing x, instrumental variables actually replace the existing regressor. So, unlike proxy variables, it actually does not have the original regressor, it completely replaces the original variable. So, now instead of x, we will be having y equals alpha plus beta z star plus u. Now, of course, this z star has to be uncorrelated to u, that is our classical linear regression assumption. Then we must have z and z star also uncorrelated, because you remember that our error term actually contains the ability also. So, this is actually u plus gamma z. So, it has to be uncorrelated to u, it has to be uncorrelated to z in order to give unbiased and consistent estimators of beta. And we also must have x and z star correlated, because we are actually finding an instrument for x. So, unless and until x and z star are correlated, the purpose is not served. So, this actually is called instrument relevance, and this assumption is called instrument exogeneity. So, the instrument must be exogenous, but the instrument also must be relevant in the sense an instrument which can replace x. So, it is, if it is completely uncorrelated to x, then it cannot be used as an instrument for x. So, for observed model y equals alpha plus beta x plus u, we will have covariance between y z star is equals to beta covariance x z, because covariance between z star and u equals to 0, which is one of the classical linear regression assumption that must the instrumental variable z star fulfill. As a result of which we have covariance y z star divided by covariance x z is equal to beta. This is z star. This is in population, but we do not know covariance y z star and covariance x z star in population. Therefore, we consider its sample analog, which is beta hat is equal to yi minus y bar into zi minus z bar star divided by xi minus x bar into zi, we can write them also zi star and zi star here minus z star bar. It should be noted that covariance between z star and u equals to 0 can't be proved. It is an untestable assumption, because u is population error and population error is not observed. So, whether covariance between z star and u is 0 or not, that cannot be actually proved. However, covariance between x and z star not equal to 0 can be proved by running a regression of x on z star such that x is a linear function of z star, and we have this the format, which is x equals theta naught plus theta 1 z star plus w, where theta 1 not equal to 0 and w is the error. Now, theta 1 not equal to 0 is important, because otherwise x will be completely unrelated to z star. Now, if covariance between x and z star is very small, then we have a poor instrument. If covariance between z star and u is not equal to 0, the deviation from beta will be large, because then covariance between y and z star equals to beta covariance x and z star plus covariance z star and u, right, because this is my original model. My original model is y equals alpha plus x beta plus u. Now, I have covariance between y z star is equal to covariance with alpha is 0 and beta covariance x z star plus covariance u z star. Now, you can see that if this is not equal to 0, then what we are saying is that deviation from beta of the observed of the estimated parameter will be large. We are now going to prove that. Therefore, if covariance between z star is equal to not equal to 0, then the sample analog of covariance y z star divided by covariance x z star does not converge to beta, but to beta plus covariance u z star divided by covariance x z star. The important difference between proxy variable and instrumental variable is that proxy variables are included in place of omitted variables alongside the independent variables like x, while instrumental variables replace x. And second thing is that once a proxy variable says z star is included, we want covariance x z star equals to 0, while if the instrumental variable is z star, then we want covariance between x and z star to be not equal to 0. Now, we consider instrumental variables in multiple regression. Suppose y is wage or log of wage, x1 is experience, x2 is education and u is the error term, which also includes the omitted variable ability. Therefore, this is our model, where this model also includes the omitted variable. The error term also includes the omitted variable, where x2 is correlated with u, and we assume that x2, that is education, is correlated with the omitted variable, which is ability, and as a result of which x2 is correlated to the error term. We need an instrumental variable for x2, say z, such that covariance between u and z is equals to 0. In the population, we must have x2 as a linear function of the existing regressor or the other regressor, that is x1 plus the instrumental variable z. So, it is not important whether we have this one not equal to 0 or equal to 0 or not, but this has to be not equal to 0, otherwise z cannot be an instrument for x2. This holds true even if the effect of x1 is partialed out. There are three moment conditions. Moment conditions are actually equivalent to OLS first order conditions, right. So, the 3 moment conditions we have, because we have one constant term, one independent variable x1 and one independent variable z or instrumental variable z. So, as a result of which we have 3 moment conditions, expected value of u equals to 0, covariance between x1 and u equals to 0, and covariance between z and u also u equals to 0. So, the moment conditions are true in population, their sample analogues are given by this. So, this is actually equivalent to expected value of u equals to 0. This is equivalent to covariance between x and u equals to 0, and this is equivalent to covariance between x and z equals to u and z equals to 0. So, this basically the 3 moment conditions and their sample analogues. Suppose there is measurement error in the independent variable such that the true model is y equals alpha plus beta x star plus gamma z plus u. So far we were talking about omitted variable problem. Now, we will talk about use of instrumental variables in the context of measurement error. So, if measurement error is there in the dependent variable, but it fulfills the assumptions of classical linear regression model, then we have noticed that there is actually no problem, because the estimates are unbiased and consistent. Now, the problem is there if we have measurement error in the independent variable. So, we observe x equals x star plus e, whereas x star is my original value or variable, where covariance between e and x star is equal to 0, covariance between z and e, that is the other regressor, and the error associated with observation x is 0, and covariance between e and u is also 0. But since covariance between x and e not equal to 0, from the observed model we have y equals alpha plus beta x plus gamma z plus u minus beta e, and we get expected value of y given x z equals not equal to alpha plus beta x plus gamma z. This is because expected value of b e given the value of x and z not equal to 0, and that is primarily because expected value of beta e given x is not equal to 0. Therefore, we need an instrument for x. Suppose x is household savings given by husbands and x tilde is household savings given by wives, where x tilde equals to x plus E1. So, now you remember that x star is actual household savings. So, one such measure we were taking from the husbands, which were denoted by x, and x is equals to x star plus e. So, some kind of errors are reported by the husbands. Now, if we consider household savings given by the wives, then we can see that with respect to husbands estimates and there is some error, that is wives and husbands estimates of household savings actually differ. Now, covariance between x tilde and x is not equal to 0, covariance between E1 and E, that is E here, is equals to 0, and covariance between x tilde and u minus b e is equals to 0, covariance between E1 and u minus beta e is also equals to 0. So, x tilde is not correlated to this error. The error term, that is E1, is also not correlated to the error which we observed with respect to our household savings given by the husbands. Therefore, x tilde could be an instrument for x, and covariance between x tilde and x is of course not equal to 0, because we want x tilde to be an instrument for x. So, it should not be equal to 0, and given this relationship it is actually not equal to 0. This is applicable when at least one between the husband and the wife has no specific tendency to overestimate or underestimate the household savings. If u minus beta e is denoted by v, then the moment conditions are expected value of v equals to 0, covariance between z and v equals to 0. So, z is the other regressor and covariance between x tilde and v is equals to 0. So, the moment conditions are fulfilled in the population, this implies that the assumptions of classical linear regression model are fulfilled, and we can have their sample analogues as previously shown. However, if both of them overestimate or underestimate, then covariance between E1 and E is not equal to 0 and x tilde cannot be an instrument, because in that case x tilde and V, their covariance will not be equal to 0, and this violates the assumption of classical linear regression model. Now, we talk about multiple instruments. So, instead of having one instrument, we can also have multiple instruments. So, if this is our original model, while y equals alpha plus beta x plus gamma z plus u, and covariance between z u equals to 0, but covariance between x and u not equal to 0. That could be because of measurement error or omitted variable problem. Now, suppose we have two instruments for x and they are denoted by z1 and z2. In order to combine z1 and z2 efficiently, we need the properties that both the instruments z1 and z2 are uncorrelated to u, so that their covariance with respect to u are 0. Suppose in the population we have this linear relationship between x and the instruments and the other regressor. So, x is equals to pi naught plus pi 1 z plus pi 2 z1 plus pi 3 z2 plus p is the error term. Now, we run a regression of x1 on z, z1 and z2. We need pi 1 not equal to 0 or pi 2 not equal to 0 or both, because otherwise x would simply depend on z. So, here actually we need pi 2 not equal to 0 and pi 3 not equal to 0. So, our null hypothesis is pi 2 equals pi 3 equals 0. Now, conduct an F test. Whatever instrument we get, we take the best linear combinations of z's. Optimal instrument for x is the expected value of x given z, z1, z2, that is expected value of x given z, z1 and z2. We have pi naught plus pi 1 z plus pi 2 z1 plus pi 3 z2. The instrument for x in the sample is actually the estimated value from this equation, or rather from this equation. The estimated value of x is denoted by x tilde. So, this is our instrument for x in the sample. The linear combination we take is the linear projection of x on the z's. Now, we talk about a generalized approach, which is also known as 2SLS or 2 stage least square. The procedure explained under the multiple instrument is actually known as 2 stage least squares or 2SLS method. So, if the model is y equals alpha plus beta x plus gamma z plus u, where covariance between z and u is equals to 0, but covariance between x and u not equal to 0 is suspected, and we have two instrumental variables for x, that is z1 and z2, and they are uncorrelated to u, then this assumption is known as exclusion restriction. Okay. The best instrumental variables for x will be obtained from the estimated model of this, that is where x is expressed as a function of the existing regressor z or the other regressor z, z1 and z2 are the two instrumental variables. If there are more regressors like z, if we have more regressors like z0, z4, z5, then all of them should have been included here. Now, where covariance between V and Z is 0, covariance between V Z1 is 0, covariance between V and Z2 is also equals to 0, and expected value of V is equals to 0. So, this implies that we must have the CLRM assumptions fulfilled. We can test for joint significance of pi 2 and pi 3 using an F statistic. We have not talked about F statistic at length till now. So, this is just a testing procedure that will be dealt with at length in the next part. In 2SLS, the first stage is to estimate x hat, that is estimate x as a function of z, z1 and z2, and the second stage is to use x hat in place of x in the original regression model. The IV estimation of alpha hat, beta hat and gamma hat are identical to OLS estimates of alpha hat, beta hat and gamma hat, because if we put x equals x hat plus v in our original model, then we have y equals alpha plus beta x hat plus gamma z plus u plus beta v. So, the estimates are same as OLS estimates. Since the composite error u plus beta v is uncorrelated to both x tilde and z, the estimates are also consistent. Now, we talk about specification test. So, this actually talks about to find out whether we need an instrument or not, right. So, this is our original model. We test whether x is correlated with or not, with u or not. So, if x is not correlated with u, we actually do not have any problem, we do not need an instrument. In order to do that, first of all find an instrument for x and estimate beta hat using instrumental variable. If covariance x u equals to 0, both beta hat OLS and beta hat instrumental variable, which is beta hat IV, will converge to beta, that is both of them will be the same. If beta hat IV is far away from beta hat OLS, then we know that covariance between x and u is not equal to 0. So, if the estimates from two SLS is same as estimate from an OLS, then there is no correlation between x and u. If that is not the case, then there is correlation between x and u. So, that was this kind of test was suggested by Hausman, and that is why it is called Hausman specification test. To determine whether the differences are statistically significant or not, it is easier to use a regression test, and what we next discuss is a test of endogeneity. So, the steps involved are find an instrument Z1, one can include multiple instruments as well. So, there can be Z1, Z2, Z3 and so on. The reduced form of x is x equals pi naught plus pi 1 z plus pi 2 z1 plus v, where covariance between v and z is 0 and covariance between v and z1 is also 0. If covariance between x and u is not equal to 0, then it must hold that covariance between v and u is also not equal to 0, because you can see that if I take covariance between x and u, then with respect to pi it will be 0. Since covariance v and z is equals to z is not correlated to u, the other regressor is not correlated to u. So, this covariance between z and u is 0. Now, covariance between z1 and u has to be 0 for z1 to be a good instrument for x. So, what I am left with is covariance between v and u. So, if this is not equal to 0, this is also not equals to 0. So, suppose we assume a linear relationship between the error terms. So, u is equals to rho naught plus rho 1 v plus w. W is an error term and covariance w and v is equals to 0 by construction. It is like CLRM assumption. And covariance x and u is not equal to 0 if and only if covariance v u not equal to 0 and if and only if rho is not equal to 0. If rho is equal to 0, then covariance u and v are not correlated. If covariance u and v are not correlated, covariance x and u are also not correlated, right. So, what we are going to test here is that whether rho 1 is equals to 0 or not. So, we include our or we modify our original model by including a rho 1 v, and this rho 1 v is actually how do we obtain the value of v? We actually do not have, we cannot observe v which is a population error from a regression of x on z and z1. What we do is that to check the endogeneity of v, we run a regression of y on x 1 x z and v hat. So, instead of v, we are having v hat, that is the estimated counterparts of v. V hat is obtained as the residual from the regression in step 2. So, we first run a regression of x on z 1 z and z1, collect the residuals, that is v hat, and then this v hat is included in our original model. So, that I regress y on 1 x z and v hat. If the coefficient of v hat is significant, that is rho 1 is not equal to 0, then of course this implies that covariance x and y is also not equal to 0. But if we observe that rho 1 is equals to 0, then this implies that covariance x and u is also equals to 0 and we do not need any instrumental variable. So, these are actually alternative ways of finding out whether there is endogeneity problem or not, whether we need an instrument for x or not. So, one was given by Hausman, which basically states that we can check for the significance in the difference between beta hat OLS and beta hat IV. Alternatively, I can also test for the significance of the coefficient rho 1 in this kind of test of endogeneity. So, these are the references. Thank you.